We say that two matrices are equal to each other if all of the elements in each matrix are equal to each other. So there's two conditions that need to hold true in order for a matrix A and a matrix B to be equal to each other. If N1 represents the number of rows of matrix A, and M1 represents the number of columns in matrix A, and suppose we have something similar for matrix B, rows and columns. And by the way, let me take one distraction here, side sort of dialogue here. So anytime you see this is just referring to the dimensions of the matrix itself, similar to like a table, right? The first always represents the number of rows, and the second always represents the number of columns. So that's just a quick note on this notation here. So anytime you see one number cross another number, that just means we have this many rows, this many columns. Okay, now getting back to our discussion on equality, remember what we said. The two matrices, there's two conditions. The first condition is that the number of rows, and the number of columns need to be equal to each other. Put differently, the two matrices need to be the same size. The second condition is that for all rows and for all columns, which I'm just using N to represent N1 and N2 since they need to be equal, M likewise. For all rows and columns, the element Aij needs to be equal to the element Bij. Okay, so that's the basic requirement for the two matrices to be equal to each other. Now, just to reiterate what we discussed in a prior video, we have some operations that we can conduct on matrices and vectors. Similar, we have to think of a single matrix or a single vector analogous to a single number. And so if I have more of these numbers and if I have more of these numbers, there's things that I can do to the numbers, right, to get new numbers. And that's the idea with matrices and vectors, right? So if you recall from your basic days of arithmetic and algebra, you know that when given any number and given any other number, let's just say in the real numbers, that you can basically do things to these numbers such that you'll get another number that's in the real numbers. And the basic things that we do to the numbers are what we refer to as operations. And you know, with numbers, we can add, subtract, multiply, although I don't like this notation. It gets confusing. Usually when we're in higher level math, we just refer to multiplication as terms being next to each other, or in parentheses, or we use a dot. That's the more, I like to call it the more mature way of writing multiplication. And by the way, division we usually write this way. In the less, what I like to refer to as the less mature way, we write it that way. But that's kind of a sloppy way of writing it. We write it this way. So anyway, we have our four basic operations. And then remember, we have other operations like taking them to powers and taking them to roots and other things. But these are at least the basic operations on numbers, right? But the thing we have to realize is that numbers are just elements in sets. And when we say that we're operating on one or more numbers, all we're doing is just taking the number or numbers and mapping it to another number, right? So when I write something like 3 plus 2, that's analogous to writing the function 2 and 3 as inputs, and I'm saying I'm mapping that to the number 5. And 2, 3, and 5, by the way, are all in the same set here. So the way that we can think about operating on numbers is by taking two numbers and basically getting a new number. Well, if we apply that same general idea to vectors and matrices, then we're doing the same thing, just on different types of elements. Pardon me. So the question now becomes, can I define similar type of operations where if you give me two vectors or two matrices, can I give you a new matrix or a new vector? And the answer is yes. So we're going to go through those. The first major operation on the elements of a set of vectors or a set of matrices is the idea of the transpose. This is the most fundamental operation on a vector or a matrix. And as we have discussed, if we have a row vector, let's say, then, and we have that row vector is 1 by n, and we have the vector a1 to an is a row vector. The transpose converts the vector into just a column vector. And so we get something different. While this was 1 by n, this technically is n by 1. Remember, number of rows, number of columns. One column, n rows, n columns, one row. Likewise, we have those are the transposes of the vectors. Sometimes you will see it written like with a dash. Some authors like to use that, including myself, might I add. The T gets exhausting to write. The dash is just fast and easy. Transposes, again, same deal for the matrices. If you have a matrix, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, then the transpose for the matrix just switches everything. And let me be clear, not all matrices are square. So for example, this is a non-square matrix, and they do have their place in applications. One thing to think of it is like number of products to produce for each individual product and individual constraints on those products, right? So they do have applications, but anyway, when you take the transpose of an n by m matrix, the transpose converts it to an m by n matrix. It flips it. And so when we have that, remember what we did last time. We take the first column and we make that now the first row. And we do that for each subsequent column. Right, and now we get our new matrix here. By the way, in terms of the matrix notation itself, a lot of people come on board with the bracket notation, but an old school way of writing the matrix is with big parentheses. It means the same thing. It's just that at some point in time, some author said, you know what, brackets look better than parentheses, but there's no difference between the two. Anyway, so here we started with a 4 by 3 matrix, and by taking the transpose, we converted that to a 3 by 4 matrix. Okay, so that all the transpose does is just literally move the rows to the columns and the columns to the rows. So that's the way we can think about the equality and the transpose operations on matrices.